Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Jadi hari ini kami ingin bentangkan task SCL MTH 3202 yang diajar oleh Prof. Madya Dr. Ilham Arif Alias. Tajuk SCL yang perlu kami bentang adalah Sylow B subgroup of A group. Jadi sebelum kami bentang, izinkan saya memperkenalkan diri saya. Nama saya Hazidan Aiman bin Hamdan 200297.
Okay, nama saya Lokman Hakim bin Zainal bernombor matriks 200581.
Saya Nurul Azrin Ardini binti Muhammad Zohan, nombor matriks 200504.
Nama saya Nurul Hasanah binti Muhammad Razi dan nombor matriks saya 2004.
Saya Khairunisa binti Abdul Hakim, nombor matrik 203064.
Saya Nurul Atika binti Muhammad Razi dan nombor matrik 202824.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So I will be presenting my task 1, which is apply theorem 1 to prove theorem 2. So the following theorem 1 tells us that let G be a finite group of order n, such that n is divisible by a prime P, then G contains an element of order P and hence a subgroup of order P. And theorem 2 is let G be a finite commutative group of order n if m is a positive integer such that m divides n, then G has a subgroup of order m. So moving on to the next slide. So let G be a finite group of order n. We have m is a divisor of n, which is m, we have P1 until Pn, which is prime. And we substitute dm with P1, so we got P1 is a divisor of n. So by using theorem 1, G has a subgroup of order P1, and we have to assume it as H. Since G is a commutative, then G divided by H is equals to G divided by P1. So now we have that P1 is the divisor of G over P1. So moving on to the next slide, then G over H is a finite commutative group, and P1 is the divisor of G over H is equivalent to P1 is the divisor of G over P1. So by using theorem 1, G over H has a subgroup of order P2, and we have to assume it as T. The subgroup of T of G over H is in the form of G1 over T. So we look at this. So G1 is equals to G divided by H times with H. We have T times H, and which is T is P2 and H is P1. So we will have P2 times P1. So the quotient group G over G1 exists, and G divided by G1 is equals to G over P1 times P2, which indicates that the P3 is a divisor of G divided by P1 and P2. So by continuing doing the similar argument, we obtain the following equation below. G n minus 1 is equals to P1 times P2 until Pn, which is equal to D. So the conclusion is that theorem 2 has been proved, by which if m is a positive integer such that m divides n, then G has a subgroup of order m, by which G be a finite commutative group of order n. So that's all from me. Thank you.
Now we go to task 2. Alright, so task 2, from theorem 2, answer the question. The question is, if m is a positive integer that divides n, does G contain a subgroup of order m? So theorem 2 says, let G be a finite commutative group of order n. If m is a positive integer such that m divides n, then G has a subgroup of order m. So to answer the previous question, I said yes. If m is a positive integer that divides n, G contains a subgroup of order m. Alright, so m divides n can be written as this. M is the divisor of n. So this also can be written as m times k equals to n, where k is any integer. So now we let G be a multiplicative group, G star, and H the subgroup of G as H star. So H be a subgroup of G. So from Lagrange theorem that has been given in the document SCL, G is a finite group of order n, and H is a subgroup of G, then order of H divides N. So order of H divides N can be written as this, the order of H, this is the notation, divisor of N. So as a note here, I said N is the order of group G. So this can also be written as H times K equals to N, where K is an integer. So M times K equals to N, since H is a subgroup of order M. So therefore, if M divides N, G is a group of order N, then G has a subgroup of order M. So to answer the question, I said yes.
Explain about task 3, which is proof theorem 3. Definition 1 said that let P be a prime. A group G is said to be a P group if the order of each element of G is a power of P. A subgroup H of any group G is called a P subgroup if H is a P group. And theorem 3 said that let G be a non-trivial group, then G is a finite P group if and only if order of G is equal to P power of K for some positive integer K. So we will prove let P power of K be the highest power of P in modulus G. The result is obvious if K is equal to 0. Since the trivial subgroup is a P Sylow subgroup, so we can take K is bigger or equal to 1, hence P can divide with modulus G. Our strategy for proving this theorem is to prove a stronger result. So G has a subgroup of order P power of I for I is between 0 and K. More precisely, if modulus H is equal to P power of I and I is smaller than K, we will show there is a P subgroup H prime in H with H prime H is equal to P. So modulus H prime is equal to P power of I plus 1. Then starting with H as the trivial subgroup, repeat this process with H prime in place of H to create larger subgroup like this. And then we reach HK, which is a P Sylow subgroup of G. And if we start with H as a P subgroup, we will have shown H is contained in a P Sylow subgroup. Consider the left multiplication action of H. On the left cosets G over H. This is not be a group. This is an action of a finite P group H on the set G over H. So by the fixed point congruence like x equal to fixed gamma x mod P, we can write it as modulo G over H equal to modulo fixed K G over H mod P, where fixed gamma x is the set of fixed point of gamma in x. And for this one is fixed K G over H is the set of fixed point of K in G over H. So here is what it means for GH in GH to be fixed by the group H acting by left multiplication. HGH equal to GH for all H in H implies HG in GH for all H subset to H. So we can write like this, and then we can get G in NH. N is normalizer for H. Thus, fixed H is equal to GH, which is G is NH. And we can get NH over H. So our assumption becomes GH implies with NH H mod P. Because H is normal subgroup to NH, hence NH over H is a group. When modulus H is equal to P power of I and I is smaller than K, the index GH is divisible by P. So it implies NH is divisible by P. So NH over H is a group with order divisible by P. Thus, NH over H has a subgroup of order P by Cauchy's theorem.
Assalamualaikum dan salam sejahtera. Nama saya Azizah Aiman bin Hamdan, memiliki 2000297. Jadi saya akan sambung membentangkan tentang konten yang keempat mengenai task 4 iaitu example of P group. Jadi saya akan membentangkan dua contoh mengenai P group. Okay, so the first example is let G be a group of order 520 equal to 2 power of 3 times 5 times 13. So letting NP denote the number of Sylow P subgroup of G. So we see N2, the element is 1, 5, 13 and 65. And N5, the element is 1 and 26. And N13, the element is 1 and 40. So suppose neither of N2, N5, nor N13 equals to 1. As we done, then N13 equal to 40. And there are 40 bracket 13 minus 1 equal to 480 elements of order 13. Similarly to N5, which is equal to 26, and there are 26 bracket 5 minus 1 equal to 104 elements of order 5. This means G contain at least 584 when is equal to 480 plus 104, sorry, 104 element. So which is impossible. Hence at least one of N2, N5 or N3, N13 equal to 1, and so G is not simple. If at least one is not simple, then it means it is a non-trivial group. So we move on to second example. So let P and Q be two different primes. Show that every group of order P square Q, P power of 2 Q as non-trivial normal divisor. So we apply the Sylow clause in the same way as the following example. Let G be a group of order G equal to 105 equal to 3 times 5 times 7. So the third Sylow set, SP denote the number of P Sylow group of G. So it as below. So S3 are equal to 1 modulus 3. So S3 have the element of 17. S5 equivalent to 1 modulus 5. So S5 have element of 1 and 21. S7 have equivalent to 1 modulus 7. And S7 have element of 1 and 15. So P and Q are discrete prime. So G are equal to P square Q. So Sylow P has order of P square. So SP equivalent to 1 modulus P, which is SP have the element of 1 and Q. And Sylow Q has order of Q. So SQ equivalent to 1 modulus Q. And SQ have the element of 1 and P. So if there are P power of 2 subgroup of order Q, each has Q minus 1 discrete elements of order Q generating the subgroup. Thus, order of P power of 2 equal to P power of 2 Q minus P power of 2 bracket Q minus 1 elements can have order of 1 P or P power of 2. This implies there can only be one subgroup of order P power of 2 on SP element of 1 and Q. I think that's all from me. Thank you.
Next, I will discuss about task 5. Task 5S is to find the definition of a maximal subgroup of a group G. Before that, given Theorem 4 says that let G be a finite group of order P to the power of R multiplied with M, where P is a prime, R and M are positive integers, and P and M are relatively prime. Then G has a subgroup of order P to the power of K for all K, where K is less than or equals to R, but greater than or equals to 0. Corollary to the Theorem 4 says that let G be a finite group and P be a prime if P to the power of F. If P to the power of N divides order of G, then G has a subgroup of order P to the power of N. So to answer the question, the definition is a subgroup M of a group G is called a maximal subgroup if elements in M is not equals to elements in G, and the only subgroups containing M are M and G itself. Explanation to the definition we did. In non-trivial finite groups, maximal subgroups will always exist because the subgroups form a partially ordered set under inclusion. Since the set of subgroups is finite, this partially ordered set will have a maximal elements. However, not all groups will have maximal subgroups, such as the rational numbers itself. Under addition have no maximal subgroups. Continue with the explanation. Let G be a finite groups where order of G equals to P to the power of R multiplied with M as in theorem 4. The theorem shows that the P subgroup of G are precisely those P subgroups of order P to the power of K. We say that the subgroup is P subgroup because G is a P group because the order is power of P. Okay, next, let P to the power of K be order of P subgroup M of G and H is other P subgroup of G. To the power P to the power of K divides order of G. Hence, elements in M is not equals to elements in G. M is said a proper P subgroup of G. So P to the power of K is the maximal elements of G for some K less than or equals to R or greater than or equals to 0. So for every P subgroup of H, elements in M is less than or equals to elements in H, and elements in H is less than or equals to elements in G, telling us that either M is equal to H or H is equal to G. Since M with order P to the power of K contains the maximum elements of G, there is no larger P subgroup of G except M and G itself, which contains M. Hence, M is maximal P subgroup of G. That's all.
Baiklah, saya akan sambung task yang ke-6 iaitu identify all Sylow 2 subgroups of symmetric group S3. Dari definition 2, let G be a finite group and P be a prime. The subgroup P of G is called a Sylow P subgroup of G if P is a maximal P subgroup of G. Jadi di sini soalan diberi adalah S3. Kita let S3 equals to G. Then the element of G is 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, dan 1, 3, 2. Sebagaimana yang kita dah belajar sebelum ni, kita boleh determine the order of G daripada bilangan elemen dalam G tersebut. Jadi the order of G is 6 since it has 6 elements. Tapi kita nak dalam term of P to the power of R darab M, di mana P adalah prime, R dan M adalah relatively prime. Jadi kita boleh determine, we can determine by order of G equals to N factorial. Saya substitute 3 kepada N menjadi 3 factorial di mana merujuk kepada S3 itu sendiri. S3 mempunyai 3 elemen set. Jadi kita kembangkan 3 factorial ni akan menjadi 1 darab 2 darab 3. Dan hasilnya kita nak hanya prime number. Jadi prime number adalah 2 dan 3 sahaja. 1 tidak termasuk. Jadi conclusion dia, we can see from the last line that 2 and 3 are prime and 2 is less than 3. So 3 is a maximal 2 subgroups of G. Hence, the Sylow 2 subgroups of symmetric group S3 are 3. Ini berdasarkan definition di atas. Terima kasih.
Alright, so I proceed with task 7. Show that every group of order 45 has a normal subgroup of order 9. So, firstly, we let G be any group of order 45 and we assume H is the subgroup of G and of order 9. So basically, we put the order of G in this formula P power of R times M, where 45 is equals to 3 power of 2 times 5, which is equals to 9 times 5. So in this formula P power of R times M, we substitute where P is a prime number 3 and R is 2 and M is 5. 2 and 5 are relatively prime. So from here we can see that G has a subgroup of order 9 from task 2 that we've discussed before, and G has a normal subgroup of order 9 since H is a Sylow P group of G, since H is the maximal P subgroup of G, since from here P power of R times M, 9 is greater than 5 and greater than 3. So we can conclude that every group of order 45 has a normal subgroup of order 9. That's all for task 7.
So the last one, we would like to reflect from what we have studied and what we have learned from this SL topic, which is Sylow P subgroup of A group. So the first one is, we explore that Sylow theorems will give us significantly more information about the subgroups of a finite group. And the secondly is, we figure out that if a group G of finite order has only one proper non-trivial subgroup of a given order, then that subgroup is normal and G is not simple. And the third one is, we learn to prove the generalization of the Lagrange theorem and Sylow theorems. And the fourth one is, we learn that M is a maximal subgroup of G if there is no subgroup of G at set M and G itself, which contains M. And the last one is, we notice that the order of a main group is a multiple of the order of its subgroup.